So, welcome back. So, now we will see with the preparation in the previous lecture how we extend the concept of Fourier transform to L2 functions. Okay. So, again let me recall the expression for the Fourier transform. So, this is f cap j integral f x I x dot j dx. So, apparently this integral does not make sense when f is in L2. Okay. So, if f is in L2, in general this integral is infinite. Okay. So, it may not be finite at all. Okay. So, so we cannot use this usual definition of the Fourier transform to define the Fourier transform for L2 functions. Okay. So, what we have seen in the previous class, that if f is in L1 intersection L2, that implies f cap is also an L2 function, and this Parseval relation f cap L2. And now we make use of this Parseval relation to extend the definition of the Fourier transform to L2 functions, but that is only in the using density arguments. So, as such, to begin with, you may not have an explicit expression for the Fourier transform. Okay. So, here is the theorem. Okay. So, for each f in L2, we can extend. So, in what sense we are extending, that is part of the proof. We can extend the concept of the Fourier transform to define f in L2, okay, with and furthermore. So, this extension. So, let me just state that this extension. So, later on we will see a different method to do the same thing. This extension again denoted by f. So, this is a unitary operator. Okay. So, let me just, if you know some operator theory in Hilbert spaces, it is fine, otherwise I just mention this is a unitary operator, okay, with this F4 identity. Okay. So, this is 1 1 on 2, and of course, it satisfies the Parseval relation. So, that is why this unitary comes. So, this is called isometry. Okay. And isometry may not be onto. So, in this case it is also onto. So, you just get this in L2. Okay. So, proof L1 intersection L2, of course sitting in L2, is dense. Okay. So, in fact, we can take continuous functions with compact support which are both in L1 and L2 and they are dense. Okay. So, as such, so there exists a sequence Fk in L1 intersection L2 such that Fk minus F converges to in L2 norm to 0. So, remember F is in L2. So, starting with an L2. But for such functions, so we already know that. So, but then Fk cap is in L2 and this Parseval relation holds. Fk. By linearity we have, so that implies, so this Fk hat minus Fl hat into is Fk minus Fl. This is by linearity. And since the sequence Fk converges to F in L2, so in particular it is Cauchy sequence and this goes to 0 as Kl tends to infinity. So, therefore, we see that this Fk is the sequence Fk cap is a Cauchy sequence in L2. And by completeness, so that implies Fk hat converges to an L2 function and that we denote it by F hat. Okay. So, this is slightly abuse of notation because we do not know what that limit is, but certainly we know it converges to an L2 function. Okay. And this we call this Fourier transform of the function F. Okay. So, we say F cap, this limit is the Fourier transform of F. Okay. So, there is little ambiguity here to begin with, but then that will clear. So, there may be several sequences in L1 intersection L2 converging to F. Okay. So, in that case the corresponding Fourier transform sequence also converges to something, and what is the guarantee that the limits are the same. Okay. So, that we have to settle it. Okay. So, suppose Fk tilde, okay, so this is different, is another sequence in L1 intersection L2, okay, and Fk tilde again converging to F in L2. Okay. And then the corresponding Fourier transforms, then the Fourier transform tilde Fourier transform converges to some F tilde. Okay, this is just a notation. Okay, so just remember that, though I am writing Fourier transform, this is notation in L2. Okay, so what we have to show is, we need to show this f hat, the earlier one, is same as this f tilde hat. Okay. So, if you need, you can use some different notation, and then finally you call, when we show that limit is unique, then you can put the cap. Okay. So, I am just writing it here, but this is easy. Okay. So, you just write f hat minus f tilde hat. So, you just f minus f k. So, this is usual manipulation. So, you write f k, no, this is f hat, f k hat, f k hat minus f tilde cap k, okay, plus f k tilde hat minus, okay. So, you take the L2 norm. So, triangle inequality, etc. So, this f k hat minus f k tilde hat and this one. Okay, all are in L2. The first term and the last term, they go to 0, and the middle term again use the Parseval relation. So, this is just f k minus f tilde k. Okay. So, but both f k and f k tilde, they converge to the same f in L2, and hence their difference goes to 0 as k tends to infinity. Okay. So, the limit is unique, and that we call it as the Fourier transform of f. Okay. So, the only disadvantage we see here is that there is no expression for the f Fourier transform of f that appears as limit of some sequence in L1 L2. Okay. But however, not everything is lost. Okay. So, this I state just as a theorem without proof. So, let f belongs to L2. So, define f n cap j. Okay, let me put that. So, 2 pi integral. Now, I restrict the domain to this n. Dx. Okay. So, since we are restricting the domain of integration to a sphere of radius, so this is for n equal to 1 to h. Okay. Since we are restricting the domain of integration to a sphere of radius n, so this integral is well defined. Okay. So, more generally I will just recall, if omega is bounded, so this is again from your integration theory, omega is bounded, then LQ omega not only subset, but it is also continuous embedding in LP omega p is less than. Okay. So that L2 function, since we are restricting a bounded domain, it's also in L1. So these Fn caps are well defined. So even for this L2 function. So then Fn cap converges to F cap. So this is obtained from the limiting process, obtained from limiting process in the mean. Okay, so this, what does that mean? So this is Fn hat minus F hat tends to 0 as n tends to infinity. Okay. Again by Weyls lemma implies there is a subsequence of Fn hat which converges almost everywhere to F hat. So not everything is lost. So still we can obtain some expression for the Fourier transform of F an L2 function. So this is akin to an integral may not converge absolutely, but however it may converge as an improper integral. Okay, so that's what is happening here, and so this is still fine. Okay. So in the remaining few minutes, let me just, since I said that thing, so but you have to fill in lots of details. This see the eigen functions, let me just mention that. You may not see this everywhere, just eigen functions of Fourier transform. In fact, we are going to define Fourier transform on very smooth functions, maybe in the next class. So as I said, this a unitary operator and satisfying this. So this means you apply this Fourier transform 4 times, okay, just like that. So you have to apply 4 times repeatedly. That's so one of the spectral properties is that then the eigenvalues or spectrum in general, eigenvalues of F contained in lambda such that lambda 4 is equal to 1. This is coming from this relation F4 equal to identity, and that set is, we know, lambda in C, okay, lambda in C plus or minus 1 plus or minus 1. Okay. So let me just mention that. I will not do the details, but okay, so there is 1 minus I minus 1 and 1 plus I. So we have already seen that this function e to the minus x square by 2, if I take the Fourier transform, I get the same thing. Okay, so that means this e to the minus x square by 2 is an eigen function corresponding to eigenvalue. And then you use the properties of the Fourier transform. What happens when you differentiate a function or you differentiate the Fourier transform? So, you keep on differentiating both sides with respect to x. Okay. So, and use the properties of the Fourier transform. So, you just get that x e to the minus x square by. So, this is the eigen function corresponding to minus sign. Okay. And then you differentiate one more time. Okay. So, this is the differentiation here, of course, sign change is there. So, you have to see that thing. So, straightway differentiation you will not get an eigen function corresponding to minus 1, that you have to combine with this the eigenvalue of corresponding to 1. So, in this case you get, so 2x square minus 1, so a linear combination. So, this x square is coming from the differentiation of this function. So, this I am again doing in the case n equal to 1. So, similar computations, of course, harder and more tedious, can be done for a general n. Okay. And this is the eigen function corresponding to minus 1. And the last one, so let me just write that. So, you do it one more differentiation. So, you get just x into 2 x square minus 3 e to the minus x square. Okay. So, what are these functions? Okay. So, keep on differentiating this function as many now, and again you continue this one, and again you get one more eigen function, etc. Okay. So, this never ending. So, you will get infinite eigen functions, and these are all called Hermite functions. Of course, I have not normalized here. So, you can also normalize with respect to the L2 norm. So, usually textbooks put that normalizing factor, but here we are doing it without normalizing factor. So, if you remove this factor e to the minus x square by 2, what you get is Hermite polynomials. Okay. So, when you put that factor, so you get Hermite functions. Okay. So, this way you also see that the Hermite functions arise as eigen functions of this Fourier transform. Okay. And you see also they are very smooth. Okay. Smooth functions. Okay. And in the next class we see how to define this Fourier transform on smooth functions. There is a class, it is called Schwarz space, and then we can also extend the notion of Fourier transform not only to LP functions, but more generally the so called tempered distributions. Okay. So, that is a discussion of the subsequent lectures. Thank you.